Hello! Have you ever looked at your scientific calculator and wondered what the buttons that say E and Lun do? Well, today, let's find out. And to do it, I'm going to try and give you a bit of background on what these things mean and where they come from, but ultimately some of the stuff I'm going to have to explain during that is things you don't need to know off by heart for the exam. So if you want to just skip straight ahead to just the basic facts that you just need to know for the exam and not interested in why these things are what they are, then you can skip ahead to that part of the video, because in the description I will provide chapters that will allow you to do so. However, if you want to stay here and hear the backstory, then what we're going to need to do is take a trip back to something you've hopefully heard about earlier on in your maths education, which is compound interest. Let's say we're looking at a really over-generous bank that's going to give you 100% compound interest applied once a year to the money that's in your account. And let's say we're applying it to something simple like £1. So what you'd have is at the end of the year, the £1 being multiplied by 1 for the 100% that you had at the beginning and you're still keeping hold of, plus another 1 for the 100% extra that you're gaining in compound interest. Therefore, that means doing this calculation, you would end up with, at the end of the year, £2. However, it could be argued that a system like this could be exploited, because it makes no distinction between somebody who puts in £1 at the beginning of the year, waits all year before they eventually get that payout at the end of the year through that interest, versus somebody who keeps nothing in their bank account all year, and then literally at the last second before the interest is due to be calculated and paid, puts in the £1, gets the interest, and then runs away with their money immediately after it's been paid. So, how could we do something to combat that? Instead of just paying 100% interest in one instalment at the end of the year, you could choose to spread those instalments throughout the year by doing, for instance, 50% interest once every 6 months. That would arguably make things more fair, because then the person who put their £1 in at the very end of the year is going to be given less interest for doing that, versus the person who keeps their money in for the whole year is actually going to get extra interest compared to what they got before. Because what that person would have is the £1 being multiplied by the 100% they originally started with, plus the 50% compound interest, but it's being applied twice, so we take that to the power of 2. If you work out what that comes to, that means that person who kept their £1 in from the very beginning of the year would end up with £2.25 come the end of the year. But again, this arguably could still be exploited. We could have somebody put in £1 just before the 6 months is up, then take their money out immediately after the interest is paid, then put it back in immediately before the second instalment of 50% interest is paid. So we can basically just continue this process by applying the interest more often, but in smaller instalments. So we could do 25% compound interest applied 4 times a year. So therefore that would be £1 times by 1 plus 0.25 to the power of 4. And when you work that out, things are starting to become a bit more lengthy to write out because there's more digits after the decimal point. It would come as just a number to 2.441406, and then it continues on. Of course, in reality, if this was an amount of money, then we wouldn't be keeping all those decimal points in there, but hey, to keep the accuracy of the number for the calculations we're doing going forward, let's keep those decimal points in there for the moment. But in general, the process that we're doing when we're doing this, if we are splitting that 100% into n installments spread throughout the year, the calculation we're doing is we're doing the 100% plus the 100% divided by n, and then we're doing that n times throughout the year. So if we continue applying this idea even further, let's say for instance you want to do 1% compound interest applied 100 times a year, you're doing 1 plus 1 over 100 to the power of 100. And if you'd work that out, then you are getting 2.70481382 truncated, not rounded, which basically means the decimal continues on longer than that and we just stopped writing because I got bored basically. And at this stage, although you might be able to see that the person who's leaving their £1 in their bank account all year round is getting more and more rewarded, the more and more we're splitting these interest payments up into smaller but more regular calculations, The benefit from doing this starts to trail off after a while, in terms of we could continue splitting up into even more payments, separated by smaller and smaller time frames, but the amount of extra money they'll gain from doing that does become smaller. For instance, if we now take this to the extreme by splitting that 100% compound interest into 1,000 installments spread throughout the year, which for your curiosity would be applying 0.1% compound interest once every 8 hours, 45 minutes and 36 seconds throughout a year, then that means we would be doing this calculation. 1 plus 1 over 1,000 all to the power of 1,000. And if you work out what that is, that's going to come to 2.71692393, again truncated instead of rounded. But interestingly, despite making that huge increase in the number of payments, or the frequency of those payments I should say, you might notice that the amount of money that they've gained by doing this has only gone up by 1 penny, which is not really that much, all things considered. And therefore it's actually worth noting that if you were to continue this process on forever, splitting the interest rates into smaller and smaller amounts, but applied in increasingly frequent time frames, then after a while you stop to see any real change in the amount of extra money this person would be gaining. In fact, if you were to do this forever, the number you would end up getting would be 2.718281828, and then more decimal points going on forever. You can see that although it has gone up from where we were at by applying this process 1,000 times a year, it really hasn't increased that much at all. It does reach what we call a limit. But at this stage, you might be looking at what we've done so far and thinking, well, okay, we've done this very specific scenario and ended up with this horrible looking number, but its usefulness extends far beyond just being something that mathematicians look at for their own amusement, because it keeps on cropping up again and again in real world applications too, ranging from things such as the radioactive decay of particles to the population growth of rabbits. And therefore, because it was something so important that does keep on getting referred to, it was decided instead of having to write out that whole horrible decimal every single time we wanted to use it, we would give it a label. And we label it with the letter E. So therefore E is the number 2.718281828, and then lots of other decimals extending on forever. But it's basically a number that's really useful for loads of things in maths. And ultimately, just like the number pi, we've just given it a letter to represent it just because it's a particularly horrible number to write out, but it's used often enough that we want to be using it despite how horrible it looks. So that's what E is, and therefore as it is just a number, you can do all the same things you normally do with numbers. You can multiply E by another number, you can add numbers onto it, and therefore if you want to write it in exact form, you would write it like so, but then you could also calculate it as a decimal using a calculator. But the most common way of all that it ends up getting used in maths is where it's being used as the base of a variable power. So, therefore, this is often how you'll see it. It'll be e to the power of x, and then we'll be doing stuff where we're plugging stuff into it or solving equations involving it, etc, etc. For instance, you might have to solve the equation e to the x equals 9. So how would you solve that? Well, the reality is some students might freak out about this because it looks complicated because we've written e there. However, we've already dealt with this scenario before in the logarithms chapter. Of course, this is a situation where the base is e, the number on the other side is 9, so therefore the rearrangement for this would in theory be x equals log base e of 9. Except the weird thing is we don't ever end up actually writing log base e of something in Maths A-level, and that's because we have a more efficient way of notating it, which is to use ln of x, often pronounced as ln of x. But it's worth pointing out that ln does just mean log base e, it's just easier to write, so that's why we use the ln notation rather than log base e notation. But why ln? Why l and n as the notation? Well, it's because ln is known as the natural logarithm, and instead of writing nl, we write ln just because of how natural logarithm is said in Latin. But there you go. That's all that's going on, so some quick examples of putting this all into practice. Let's say you want to solve these two equations. Well, the first one, very quick and easy. All you've got to realise is this would normally be solved by using log base e, but instead of writing log base e, we write ln. So therefore the solution to this would just be x equals ln of 5. That would be the answer in exact form, but again you could type that into a calculator to get what that is as a horrible decimal. For question 2, well, we're going to use ln again, but in order to be able to use it, we first have to rearrange it, so the e to the power of something part is isolated by itself on that side of the equation. So we've first got to add 7 to both sides in question 2 to get a 27. Then we divide both sides by 3 to end up getting 9. And now we can use the natural logarithm, which will tell us that 5x equals ln of 9, and therefore we can divide both sides by 5 to get the answer in exact form being x equals 1/5 lots of ln 9. And then of course sometimes we have to go in reverse. So in this case, in question 3, we've been given that ln of x equals 4. Well, therefore we don't like the ln now because it's not something we can type into the calculator because it's got algebra inside. So therefore getting rid of it, we can rearrange to get x equals e to the power of 4 in exact form. That is of course just making use of the rearrangement we'd already used in the logs chapter, which is a to the power of something equals b, rearranges to x equals log base a of b. And it's just that because log base e is ln, that's how we ended up writing it like this. And on to question 4, it's the same idea basically. We want to get rid of the logs, or the lns, and therefore to do that we're going to make use of this rearrangement up here again by rearranging it to the point where we've got all the logarithms, or lns, on one side grouped together into a single logarithm, and anything that isn't a logarithm on the other side of the equation. So therefore in this case we'd add ln of x onto both sides, so the ln of x and the ln of 4x minus 1 are together on the same side of the equation. We could then use log laws to combine the logs into a single log, and to do that you end up multiplying the two things inside the logs. So you end up with x lots of 4x minus 1 if we make good use of enough brackets. That does of course just simplify to ln of 4x squared minus x, and then we can get rid of the log using the same rearrangement we had before, which would tell us that 4x squared minus x equals e to the power of 3. This of course is just a quadratic now, although it looks really horrible because you have e to the power of 3 there. That is just a number. A horrible number, but a number nonetheless. So therefore it's a quadratic with an a coefficient of 4, a b coefficient of minus 1, and a c coefficient of minus e to the power of 3. So then of course you're going to want to use the quadratic formula to solve it. So therefore we would have x equals minus 1 plus or minus the square root of minus 1 squared minus 4 times by 4 lots of minus e to the power of 3, and then we're dividing all of that by 2 lots of 4. If you type that onto the calculator, the two answers you'll get as decimals would be 2.37 to 3 significant figures, or alternatively minus 2.12. Cool. Okay, so that's those questions done, and that is an introduction into what e is. It's just a number. What ln is, it's just log base e, and therefore we're going to be using these things a lot in various future aspects of Maths A-level. Okay, that will do us for today. Hopefully you found today's video useful, and I'll see you in a future video. Goodbye!